welcome to our first lecture and our first unit or section or level or stage. And really what we're going to start with is our scientific thought and matter. So first place to start would be why science. So this is an activity I like to do in a larger classroom and have different people describe what they think a pessimist would see here versus what an optimist would see within this image. And we get a variety of different answers that pop up, but I'll try and summarize some of what I've had students say in the past. A pessimist might go through and look at this and say, well, they see a bunch of calories, too much sugar, because sugar is unhealthy. They might go through and say, well, there's fat within that pie crust. Okay, that's not particularly good. Maybe they have an allergy to strawberries. Okay, so we're looking at all those kind of negative aspects behind it. An optimist might go through and say, well, it's just a freaking pie. Okay, like that's just freaking great. They might go through and yes, say there's sugar. Okay, I see strawberries. Strawberries are fantastic. I love strawberries. Those are the greatest things on the planet. So there's a variety of different ways that we could go through and interpret what we're seeing within this from those different perspectives. And then we would kind of zero in on, say, what would a scientist go through and see, and try and think about how a scientist might envision this. And in my experience, what a scientist sees within this is still the same things that are coming up with a pessimist and an optimist, but they're going through and saying that they can do it better. So there's something about this pie or this object that we're studying, and we want to figure out how it works so that we can do better at it. So they might go through and say, well, those strawberries aren't particularly ripe strawberries, so we want in-season strawberries. We could go through, if you haven't heard of them already, there's these super fancy, expensive, like $2,000 per strawberry coming out of Japan. So you could go through and make a strawberry pie out of that. You could go through and say that the sugar that was originally in the recipe was white sugar. Well, white sugar doesn't really have a lot of flavor, so instead we're going to use, I think I've got it, Demerara, something like that. Demerara sugar or brown sugar. They're going to change some of that flavoring. I went through and looked at the pie crust and said, oh, they just use white flour. I'm going to use whole wheat flour because I'm going to make it healthier. I don't know why you'd make a pie healthier, but these are the things that a scientist would kind of evaluate. What are the components that go into this? What are those different phases? What are those different controls? And how can I change and tweak those to make it better? And some people might say, well, that sounds an awful lot like, I don't know, a chef. Well, yeah, cooks are ultimately, depending on how you're going through and running it, doing the same thing that a scientist would be doing. So how do we structure this? How do we organize this? And so this is where we come up with a scientific method. And if we're going to try and learn something, in particular something new, if that's our ultimate goal, we need kind of a structure behind our process and how we would navigate it. And typically when we talk about the scientific method, it starts with an observation. An apple just hit me on top of the head. Okay, what does that mean? How did it fall on top of my head? Why did it fall? What caused it to fall? Those are all kind of observations that would ultimately lead to a hypothesis. The hypothesis is then formulating kind of an explanation for why you think that's happening. It's kind of a guess that we would then need to be able to test via an experiment. And so the hypothesis has to be testable. And this is a critical aspect of our scientific method. We can't just hypothesize that something is going to happen and then say, oh, well, now, of course, it's real, unless we have an experiment that allows us to actually test the validity of the hypothesis. And again, in a real class, this is where I would like to have students say, oh, well, what comes after the experiment? And 9 times out of 10, I'll hear people telling me about theories and things like that. And one of the dirty little secrets behind science is that that's actually not true. We don't go from an experiment to a theory. We actually go to failure. And so most scenarios or most scientific processes result in failure. The experiment failed. Something didn't allow us to understand what was happening with our hypothesis. And so we go back to the drawing board, we tweak our hypothesis, we adjust our experiment, and we run that process again. And one of the things that I find particularly interesting behind this is that as we continue to run this process, and we go, okay, well, it didn't work that time, so we fixed it. And we say, okay, well, what comes now? Well, it turns out failure happens again, and again, and again, and again. And so scientists, there's a definition of insanity that you repeat the same action expecting a different response. Scientists are kind of insane in that response because they are repeating the same action and hoping for a different response, but it's not the exact same action. What they're doing is they're tweaking, they're making adjustments to both the experiment and the hypothesis, control the variables, so that they can better see results that come out of that. And if all of that works and comes together the way that they would hope, then we could navigate onto a scientific theory or natural law. Scientific theory is something that gets constantly revised, because what can happen from that experiment is we may draw a scientific theory where we've got some idea of what's going on with it, but it doesn't fill out the complete picture. So somebody else says, well, what if we think about it this way? So they create a new hypothesis based off of that theory, and they create a new experiment. If their experiment answers the original hypothesis better, then the theory gets tweaked and it gets adjusted based off of the experimental evidence. Natural laws are kind of absolute truth, if you will. They're kind of facts. These are natural observations that we can't change, or we can't change yet, at least. And we're kind of running out of opportunities within that realm. For the most part, most of science has settled into that scientific theory. How do we learn and design experiments that allow us to continue to navigate and grow the scientific process? So where's chemistry's role in this? Because there's lots of different science fields. Mathematics and physics on the, I guess we could call it the hardcore numerics side of this. And then we have the biology and other stuff on kind of the other side, which can, but not always, take a step back from the numbers and the mathematics behind it. And so what you'll hear chemists tend to say is that they're the bridging field, that they're the ones that bridge the mathematics, the physics, the hardcore theory, and tie that to the larger impact world that we might see within a biology class. All fields are going to say they're the bridge, for the record, but chemists do seem to have this kind of foot in two worlds. What is that theoretical aspect in the mathematical side, and then also how does that apply to the real world, and how can we use that to understand these kind of macro scales? Chemistry as a field will further subdivide out. So I would argue you're in a class right now that I would say is actually general chemistry, not so much fundamental. Fundamental is really just an overview of general chemistry. And general chemistry is also an overview of all these other little subcategories within it. And within those categories, we get things like organic chemistry, we get biochemistry, we get inorganic, and we get physical. So organic chemistry, I'm trained to teach organic chemistry more than anything else. And so one of the things that always kind of bothers me is that organic chemistry is where you would put Breaking Bad. So that show and how we make drugs, yeah, that's kind of the organic field. That's changing a little bit, and we're starting to actually bring in that it isn't just about drugs, that we can actually make interesting items from organic chemistry. Biochemistry is going through and looking at really the bio side of it, but the why the bio side of it is happening. So you're looking at the chemicals involved in each of those pathways. So if you've taken a bio class, they will have tried to whirlwind through chemistry because they end up using a lot of the aspects of chemistry in their discussions. And then we get inorganic chemistry. And inorganic chemistry takes a step away from the bio because it's not biology and it's not organic. Both of these are kind of grouped similarly. Both of those are usually studying carbon and hydrogen. I'm going to try and be better about my handwriting in the future. Some carbon and hydrogen forms. Inorganic pretty much just says, well, there's a whole lot more elements than carbon and hydrogen. Let's study all of those. And so your inorganics tend to be studying metals, but you'll find that there are chemists that will study bio-inorganic. So how does the biological chemistry intersect with the inorganic or the metal chemistry, which it does a lot. And then physical chemistry, as the name might suggest, ties back pretty heavily into the physics. And so what you're looking at within physical chemistry, I would probably break down into thermodynamics. So how does heat play a role, and how does heat change chemical reactions? And then quantum, which as you may have heard in pretty much all of our Marvel or DC universe, quantum is what's used to describe anything that they can't define, which is kind of true in a grand scheme. And that would be our physical chemists. So each of these fields kind of subdivide out to study different aspects of chemistry in different roles, which is kind of fun. Which then sets us up with what can we do with this. So our scientific method was about observation. So we could go through and break observation down into kind of two major categories. So we have a qualitative category, okay, and as the name may suggest, what we're pushing into there would be kind of the quality of it. So if we think about quality, we'd think about, in this picture, how fine that wool is. Okay, fine, or we could go with clean that wool is. We could go with the color of that wool. The color was, I'm going to artistic license and call that white. We could then also potentially think about the quantitative side of it. And so the quantitative side, again, is going to boil down, if we look at our roots, down to quantity, so how much. So we could look at that and say, well, that is 2 sheep. That would be identifying a quantity of that item. You could also go through and say, maybe you were a butcher and you look at that and you say, well, that's 150 pounds of usable meat. I don't know. Or we could switch that around. Instead of being the murdering the animal, we could go through and say that we're going to need 1,000 pounds of, let's say, hay, to keep those animals alive in a year so that we could then harvest the wool. So when we're thinking about observations and how we're navigating chemistry, we want to be cognizant that we do have 2 areas for observation, both our qualitative and our quantitative. Both are very, very important. One of the things that you'll find as you navigate through our labs is that the quantitative tends to take dominance, particularly early on. That quantitative observation tends to be what we study the most in general chemistry, as we're dealing with all the mathematics and how we quantify all of our reactions. But realize we do also address the qualitative side of it, and it can be as important, if not more important, than the quantitative. So make sure to keep that in mind as you go through and navigate our content. So let's look at some qualitative observations so we can start narrowing the field a little bit. And we could ask this question, well, what is 70 to 80% the composition of life, or even the planet? Well, I've got a lot of blood, right? Well, what is blood? Well, blood cells and things like that that are absorbing oxygen. Well, how are they transferring the oxygen? Well, they got the cells, biological systems. Well, what's in those biological systems? What's our cells? Well, what makes up the cells? And if we start to drill into that a whole lot, what we'll end up discovering is that about 70-80% of life, as we know it on this planet, is made up of water. And water is a fascinating substance. Water can appear in multiple different phases. And I know these pictures aren't the greatest, but I did try to come up with something representing a solid, a liquid, and a gas for each of those individual phases of water. And so it's a really neat phenomenon that we could go through and start to qualitatively classify the matter that we see around us. And that's kind of neat. As we go through and push further, of course I knew that was going to happen, our individual phases can then come up with different descriptions to go over them. So we could talk about the shape. Well, if we think about a solid, what happens with its shape? Okay. Well, what do we mean by what happens with its shape? Well, if I took a solid and I went and put it on a counter, what happens with its shape? Well, it stays the same. Okay? It's a static shape. If I went through and took a liquid and I put the liquid on the counter in front of us, what would happen with the liquid? Well, it would change. It would kind of mutate, vary. Let's go with vary. Mutate's a little weird. Okay, and it would take the shape of whatever container held it. Okay, so this is a variable shape. So just by making that qualitative observation, we could start to differentiate solids from liquids. And if we push to the gas, what happens with its shape? Well, if I don't see gas, but we could observe the effects of gas. Say with a balloon, we can blow air into a balloon, and we could see that the shape would take on the amount of gas that was present. So again, we encounter a variable system. The gas is going to fill whatever object it's in. If we now push the volume, well, the volume for a solid, once we have it, is again going to be static. Length, width, height. So think about it as just a cube. It's going to stay that same volume. If we go through and shift to the liquid, well, the liquid gets a little bit tricky here, because if we consider what happened to it when I poured it into one container, well, it changed its shape. Dang. But is it changing its volume? If I had a tall, skinny container with a liquid in it versus a, whoops, that was supposed to be a short container. See, does that work? That didn't do what I wanted it to do. If I had a short, wide container with that same liquid, would it occupy that same level, that same height? No, it wouldn't. Well, what would it actually occupy? Well, it would actually occupy a volume, an area less than that, because the volume of the liquid stays constant. Okay, it's static. Well, what about the volume of a gas? Does the volume of a gas change? Okay, well, I could blow up that balloon, right? And as I put air into the balloon, I now have gas particles into it. But what if I heated up that balloon now? Well, it starts to change, right? As you heat that up, the balloon gets bigger. If we talk about hot air balloons, those are skinny little things. When you turn on the heat on them, that's what causes the air to kind of expand and push outwards. So a constant amount of gas would occupy a different volume, because the volume of the container is what's actually defining it. So the volume of our gas, interestingly enough, is variable. Which then moves us to compressibility. As we compress or try to squeeze it, what do we see happen? Okay, well, again, with our solids, they tend to be not compressible. Okay, pretty extremely so. Physical chemists in the world can go through and tell me that that's not entirely true, because it isn't. They do have some compressibility, but it's very, very limited. The same thing can be said for the liquid. When I push down on that liquid, what ends up happening? Well, it squirts up the other side. But if you can create a system where you can push the liquid, what you'll find if you took a syringe barrel and held it closed, that when you try to push down on that barrel, then it doesn't really move, because liquids don't compress. So they have a little bit of compressibility, but similar to the solid, there's not very much. Okay, and what happens with the gas? Those are highly compressible. This is why we can move gases around, and we see tankers of the road talking about compressed gas cylinders. Because what we've done is we've pushed so much gas particles in there that volume between our particles now starts to shrink. Okay, so we can get some big compressibility there. So we'll call this, I guess, large compressibility, or a lot, perhaps. And those now give us an idea of our different phases that we could see: solids, liquids, and gases. Well, what other qualitative observations could we start to navigate? Well, we can now expand this out to now all forms of matter and say, whoa, I see a solid there, I see liquids, I see gases. And now we want to think about, well, are those all the same? So when I look at solid water versus solid gold, what does that mean to me? Okay, what is that difference? And if I look at solid table, for that matter, I can knock on it. You may not be able to hear that. But when we look at a solid table, how is that different from solid gold or solid water? And so what we start to do is now subdivide or subcategorize our primary topic of matter and say, well, what else could we go through and do? And so that's where we're trying to kind of branch this downwards into those different characteristics. And so we'll talk about mixtures where you have multiple, because we haven't defined them yet, multiple pieces of matter that are spatially near each other, but that you could physically move away from each other. So if we looked at a saltwater solution, what would happen? Well, could I separate them from each other? Well, if I boiled the water turns into a gas and it leaves behind the salt. So if you've ever experienced it, oh, I'm going to make pasta tonight, and you set out your pot of water to boil, and then you forgot about it, you went and did laundry or something else, and you came back and you're wondering why your house was on fire, you go back and look at that pot, and what you would see in it is a ring of white, a white solid. Those were all the dissolved materials within your water. Okay, so those would be spatially linked. A pure substance would be chemically linked. So if we drilled into that water, let's just look at just that water. Well, what is water? And for those of you being like, well, I don't know, it's my first chemistry class, I don't know this. I know, this is where this conversation gets a little bit weird. But hopefully, we might have heard that water is H2O. Well, what is H2O? H is hydrogen and O is oxygen. Those substances are chemically linked to each other, which means if I add heat or change pressure, I can't go in and remove that hydrogen atom away from the water. I can't remove the oxygen away from those hydrogens. Those have to undergo a chemical reaction. That chemical reaction is that chemically linking as opposed to spatially linked. So spatially linked, think about our bulk physical process. Can you tweezer them away? Can you change the phase of the substance to get them to separate away from each other? Chemically linked, those are now moving into a world that you probably haven't dealt with much, and that's where you would actually have to change the chemical composition. You have to run a chemical reaction. That's significantly harder. If we now further subdivide each of those two categories, what we can see is that we can get a mixture. Well, mixtures can be spatially linked and be either heterogeneous or homogeneous. Your hetero is saying multiple things. Your homo is saying single thing. But if they were different, things like water versus salt, isn't that always heterogeneous? Well, really what these are talking about are the phases. Okay? The phases that we talked about with solid, liquid, gas with our water. So if we're talking about heterogeneous, this is really saying many phases. Whereas our homogeneous is saying one phase, or same phase, if you will. So if we're now looking at an object, a thing, we could go through and now classify that as heterogeneous or homogeneous. So we looked at the salt water. What happens when you add salt to water? Okay, if I had two containers in front of you, one with salt water and one with water in it, would you know without drinking? Well, no, because visibly they look the same. There's no visible separation between those phases. Salt water would be an example of a homogeneous system. Whereas salad dressing, how do we make salad dressing? Salad dressing is a mixture of water and oil. Well, at its basic level. And water and oil will visibly separate away from each other. You say, well, but they're both liquids. Isn't that the same phase? But they're distinguishable phases. There's a visible separation between them. Okay, so that visible aspect is kind of critical behind this. What makes it even trickier is, what if we asked a blind person to differentiate between these? Well, how would they be able to figure it out? This becomes one of the problems with, for that matter, a lot of sciences, is that it all relies on our observation. And if our observation is somehow limited, it limits our ability to make broader conclusions about those systems. Right? So we have to consider that as we navigate this class, and for that matter, any science class. If we shift over to the pure substance, okay, chemically linked, we're looking at a pure substance where we've got compounds, and this is now at least two elements. Well, what are the elements? We'll look at that in a second. And then you've got elements, which is only one type. Okay, so if we went through and looked at a diatomic, two di, roots as two, and then atomic, meaning atom, a diatomic element, we could get something like bromine, which would be Br2. I would specify that 2 in the lower right-hand corner to tell me something about the amount. Well, that's one type of element there. There's just two bromines, so I'm going to call that an element. If I go through and look at the compounds, they have to have at least two elements. So compounds, we could go through and say HBr. Well, H and Br are different elements, because of how our symbols have changed. That would now be a compound. I could take HBr and I could dissolve it in water. When I dissolve it in water, it becomes HBr. Well, dang, that's not very useful. How do I know it's a mixture? I would specify that mixture, again, in the lower right-hand corner with an AQ for aqueous. More content we'll learn later on in the semester. So HBr mixed with water is now actually a mixture, not a compound anymore. Because I've taken two compounds, water and HBr, and put them together. And if I tried to now differentiate which one was visible or invisible, what we would find is that HBr dissolves fully in water, which sets us up with the homogeneous solution. These different classifications can be very challenging to go through and navigate, particularly early on in the semester. As we encounter examples both in class and in the homework, I encourage you to send me or your instructor, if we have somebody else using these lectures, to figure out why they would differentiate in one place versus another, because it can be a challenge to go through and nuance. With that, we can now start to look a little bit more into our elements, like hydrogen or bromine or oxygen, and what we would try and do is subcategorize them out even further. And one of the first categories that we come up with is this concept of metals versus nonmetals. And so what we've got listed down below is actually a clear delineation. These descriptions all apply to the metals. Come on, pen, work with me. Our metals, and these descriptions all apply to our nonmetals. So what we went through and did was made qualitative observations in some of these cases and started to categorize. And so what we noted is for our metals, most of them are solids, whereas our nonmetals are solids or gases. Okay, so that starts to stand out. That phase is dependent on temperature. So when we're talking about solids and gases, we're talking about as we would experience them in kind of our standard state. If we look at the material itself, the metals have a luster or a shine. The nonmetals are dull, and so they don't shine, they just kind of look flat. Metals are malleable, so when you hit them, okay, they just deform. Nonmetals, when you hit them, they're brittle, and so they shatter. So that's not an easy thing for us to ask about on a test, other than just, do you know those words? That would be more an observation that you would see in the real world. We can then move into conduction, and what we would note is that our metals conduct heat and electricity fairly well. Again, this is a testable observation that we're now making. We would try and put electrical current in and see, did that current pass through? We put heat up next to it. Do we feel the heat passing through? Okay. Our metals tend to do that. The nonmetals are non-conductors, so they tend to not allow the passage of heat or electricity. Density. Density is actually a conversion factor, which we'll talk about much later in the semester. And density, we'll just bring in a new color for our density, is the relationship between mass related to our volume. Okay, so the fun test that we could go through and do is, which one would you rather be hit with, a pound of lead or a pound of feathers? Okay, well, they weigh the same thing, they have the same mass, but we'd probably be rather hit with a pound of feathers, because the feathers are being spread across a larger area. That impact wouldn't hurt as much. So what we find is our metals have high mass to volume ratios, and our nonmetals have low mass to volume ratios. We can then go through and look at melting points. Okay, melting points are now quantification. So we've got high melting points for our metals, they're solids, and for our nonmetals, we see low melting points, which is why they're gases. We can talk about their chemical reactions. Metals tend to react with nonmetals. Metals can mix with other metals, but they tend not to chemically react. Nonmetals, on the other hand, will react with anything and everything. You put them together, they'll do a chemical reaction. And so we get our elements dividing out into those categories. So I've provided some pictures up at the top. This would be a good opportunity to pause and have you think about which one of those images ties to which material. And now that you've had an opportunity, we could go through and say, well, these two look shiny and they're solids. And since they're shiny, that ties in with the luster and the solid. Okay? We know nothing about any of those other categories, so really those are not relevant to us. And if we go through and look at the other two, those other two we're seeing a not solid, okay, or we could say liquids. These aren't shiny at all. So those would kind of match the dull and the less likely to be solid category. And so what we're looking at is different materials. Kind of neat. And let's go ahead and give you another opportunity to kind of test yourself through it. What do you see with these? So now you had an opportunity to go through and guess. This first one does not look particularly shiny. And since it's not shiny, we would hazard a guess that that would be a non-metal. That next one is very shiny. So since it's shiny, we would go through and hazard that that's a metal. The last one, very shiny as well, we'd probably call that a metal. And we might be like, well, what the heck is going on with that purple thing? That purple thing is a tricky one, but it's kind of the system that we're looking at. We've got a glass tube with an electrical current running through it. That current causes the gas inside that tube to glow. That's a non-metal. Okay? And then, to make matters worse, because we always make matters worse, we could go through and take a look at these substances. And if we go through and try and determine these substances, what we'd find is that they don't actually classify as metals or non-metals, which is really frustrating. Well, but they're all shiny. Shouldn't they be metals? Well, remember, it's not just whether they shine or whether they don't. We also have to deal, with all of these other categories. So the brittleness, the conducting of electricity, the density, the melting points, their chemical reactions are also things that contribute. And what we find for these three particular examples is that these three share properties of all of the above. Okay? So they're all solids, but they don't conduct electricity quite the same. They're malleable, or they're brittle, okay, or their density is off. So they don't fit either the metal or the non-metal category. So we end up calling those, as a tip-off if you didn't notice it, metalloids. So our metalloids straddle that border between our metals and our non-metals, which then gets us good opportunity to set us up with a periodic table. The periodic table is now something that you will always have with you. Why? Because you're now officially a chemist. So you need to be familiar with the periodic table. The periodic table holds a lot of this information in it. It should give us information about solids, liquids, and gases. That depends on the format of the table, unfortunately, and this version doesn't give us that clue. But it does give us information about our metals and our non-metals. And so if you could recall from some of your background knowledge a material that you thought was a metal, you might, as a guess, come up with gold, AU. Or you might say silver, AG. Or you might say iron, Fe. Okay, well, all of those elements, you'll start to note, happen to be towards the left-hand side of the periodic table. I just realized that I color-coded this backwards from our previous slide. So the left-hand side, the further left you go, the more metallic you are. Well, what does that suggest then about the further right? Well, the further right you go, you have the non-metals. Okay? Like oxygen, neon, bromine are all examples of non-metals. And where do the metalloids fall? Well, the metalloids are then going to fall in that exact diagonal, it turns out, that middle space between the metals and the non-metals. Depending on the periodic table you're looking at, that information is coded because they show it as a slightly different colored line. You can remember it as the staircase down the periodic table, because you'll sometimes see that. Again, this periodic table doesn't have that information encoded in it. Okay, but what this periodic table has is names. Okay, and you might say, well, why don't I always use this so I always know the name associated with the symbol? And I would argue that the more time you spend looking up the name of the compound associated with its symbol, the less time you're actually spending solving chemistry questions. So you are highly encouraged to spend some time to actually memorize at least some of our elements. Okay, for a reference, I've provided a link, which is not in the video, but maybe I'll see if I can figure out a way to get that publicly accessible for anybody that's watching this outside of our classroom. And that would be our elements for memory. A colleague has now made that document very, very fancy. It should be embedded within your class. If it's not, it's less fancy, but you should spend some time to memorize it. For everybody on the, just in general watching this, I would argue you're looking at 1 through 36 should be memorized. This isn't because I want you to memorize 36 different things. It's because you're going to see those elements a lot. And since you're going to see them, you should know them so that you can use them faster. Okay, when you look at the document, you'll see that there are significantly more than 36 that you're asked to memorize, because there's other ones that you'll see commonly, like gold and silver, show up fairly frequently. You'll see iodine, you'll see cesium, barium, rubidium, strontium. You'll see xenon every so often. My wife sees indium all the time. So there's other elements that you'll want to spend some time to memorize so that you know what the symbols are and you know their names. That'll speed your process along. If we navigate to a slightly different periodic table, okay, this periodic table is one that we commissioned to have built, and you'll note that there's some kind of subtle differences between it. So for instance, when you look at this table, what you'll probably see is that everything gets kind of smushed together. There's very little white space in between things. You'll see a little bit of white space here, right? And that's ultimately because this set inserts right there, but then it would turn into this wicked long periodic table. So we boxed it to make it look a little bit easier. But you don't see a lot of white space, everything's smashed together. Okay, well, why is that? It helps to kind of make things boxier and easier to see, but we lose some kind of information within it. So for instance, you see that helium and hydrogen have this kind of white space above that periodic table. You'll note that there's a slightly larger white space, in this case gray, centering in between there. And that's because it's trying to pull attention to and separate out different sections of the periodic table. Those sections are going to become more relevant later on in the semester, and so it is important to be able to see and find those, which is why I want you to see this periodic table. The other reason why I want you to see it is you'll also note that we've got colors. We've got red, we've got blue, and we've got black for our fonts. And since that can be challenging to understand why there would be colors, this is where you should frantically look for special keys that tell you the meaning behind them. The elements that are all black are all solids. The elements that are red are gases, and the elements that are blue are liquids. The outlined, I actually even missed that one in my summary, which I'm now going to circle in green. Those outlined ones are all synthetically prepared. Okay, so that means they're man-made. If we're talking about elements to memorize, you probably don't need to memorize any of those because they're man-made. We have very small concentrations of them. We're probably not going to talk about them much, so you don't need to spend your time to memorize them. And with that, we've now completed what feels like a very long lecture, but hopefully it's summarized those basic components of all of our individual pieces and should give you a better idea of what we're trying to do as far as our scientific method goes. Thanks for watching.